At first, Russian air defenses reported nothing unusual, no strike package, no missile barrage, no obvious threat. Then, the radar feeds began to behave strangely. Missiles were launched at shadows, and seconds later, a transport aircraft was burning on the apron. This wasn't a conventional attack, and it wasn't supposed to be possible. Military analysts initially dismissed it as a systems glitch, until the footage emerged, and it became clear this was a kind of air battle we had never witnessed before. The drones did not survive by simply hiding from radar. They survived by actively disrupting the way radar thinks. Traditional air defense systems are built around an assumption that real targets behave consistently. An aircraft has a stable radar cross-section, a predictable velocity, and a movement pattern that fits into known categories. What happened in this engagement shattered that assumption. The Ukrainian drones presented radar returns that refused to stabilize. One moment, they appeared roughly the size of a small vehicle. The next, they collapsed toward near-zero signatures, only to reappear again seconds later. This was not random noise or poor sensor performance. It was a deliberate manipulation of radar logic designed to force the system into constant reclassification. Every time the radar software failed to match the return to a known profile, it restarted its evaluation process. Each restart cost time fractions of a second that accumulated into critical delays. Modern air defense radars are optimized to filter out clutter, especially over the sea, where wavetop spray and reflections generate massive background noise. The drones exploited this environment by flying at altitudes where radar discrimination is already strained. Their composite airframes absorbed and reflected radar energy, unevenly producing inconsistent echoes that confused automated tracking. The system was trapped between two possibilities: treat the contacts as clutter and risk missing a real threat, or treat them as real and waste attention on something that might not be dangerous. That hesitation was the opening the drones needed. This represents a fundamental shift in how stealth works. Instead of trying to disappear, the drones stayed visible but unreliable. They did not seek invisibility, they sought ambiguity. In doing so, they turned the radar's greatest strength, its precision, into a weakness. Precision demands clarity, and clarity never arrived. The system was forced to guess, and every guess delayed action. In modern drone warfare, confusion is no longer a byproduct of battle. It is engineered, controlled, and deployed as a primary weapon, capable of neutralizing defenses without ever destroying them directly. What made this phase of the attack especially effective was not speed or surprise, but a precise understanding of how air defense systems decide what matters most. For decades, doctrine has trained radars to treat altitude as a proxy for danger. High-flying objects move faster, cover more ground, and historically represent aircraft or missiles capable of delivering decisive strikes. The Ukrainian decoy drones exploited this hierarchy with deliberate restraint. They did not climb aggressively or chaotically. They ascended just enough and just long enough to cross the invisible threshold where radar logic stops asking "what is this?" and starts declaring "this must be stopped now." In that moment, priority rules activated automatically. The system did not consult a human operator. It followed its internal ranking model, assigning the climbing contacts urgent status, while quietly demoting the low-flying drones that posed the real threat. By briefly presenting radar profiles that resembled conventional aircraft, larger cross-sections, steady climbs, consistent velocity, the decoys redirected the entire engagement upward. Interceptors designed for fast, high-altitude targets were committed exactly as doctrine demanded. From the system's perspective, nothing unusual was happening. The wrong targets were not chosen because of error, but because the rules were followed perfectly. This was deception aimed not at human perception, but at software logic trained on decades of air combat assumptions. The drones did not outsmart the operators. They outperformed the decision trees that shape modern air defense behavior. Some observers may see this as an unnecessarily risky maneuver, arguing that any climb exposes drones to detection and destruction. Others might contend that it was the only viable way to fracture a layered defense without overwhelming force. What is difficult to deny is that this tactic turned altitude, a traditional vulnerability for small drones, into a tool for control. It raises an uncomfortable question about whether our most trusted automated priorities still reflect today's threats. I'm curious how you see it. Was this clever exploitation, dangerous improvisation, or an inevitable evolution of drone warfare? Share your perspective in the comments. The imbalance in cost between the attacking drones and the defending missiles is often discussed as an economic problem, but in this engagement, it functioned as an operational weapon. Each interceptor launched was not just a financial loss. It triggered a cascade of mechanical and computational consequences inside the air defense network. When a missile leaves its launcher, the system must shift power, reassign tracking priorities, and often reset or recalibrate sensors affected by exhaust vibration and temporary signal saturation. These processes are built into the design and normally occur so quickly that they are barely noticed. Against conventional aircraft, the timeline works. Against slow, persistent drones, it becomes a liability. Every launch forced the defenders into a brief period of reduced awareness. Radar filters adjusted, tracking histories were rebuilt, and engagement geometry narrowed as launchers committed to specific arcs. For a few seconds at a time, the system was not blind, but unfocused, unable to see the full battle space with clarity. The drones did not need to destroy the defenses. They only needed to keep them busy. By absorbing interceptors that were vastly more expensive and complex than themselves, the drones induced a form of system fatigue. This fatigue was not about running out of missiles, but about accumulating micro-delays that gradually eroded coordination. Time became the real currency being spent. Each reset consumed seconds. Each reload timer constrained firing options. Each engagement reduced flexibility elsewhere in the defensive layout. Geometry collapsed inward as launchers were locked into narrow cones, leaving gaps that could not be covered simultaneously. Sensor coherence suffered as different layers of the defense rebuilt their situational pictures at slightly different moments, creating mismatched timelines and uncertainty about what was already engaged and what remained inbound. In this context, cost asymmetry reshaped the battle long before any stockpiles were exhausted. The drones exploited the fact that complex systems grow less resilient as they work harder. By forcing repeated high-effort responses to low-cost threats, they transformed sophistication into friction. The result was not a dramatic collapse, but a gradual loss of rhythm, where the defenders were always reacting, always recalibrating, and never fully synchronized again. One of the most consequential vulnerabilities exposed in this engagement was not a gap in coverage or a lack of firepower, but the quiet routine moments when the radar system had to reset itself. Every missile launch initiated a chain of internal processes, filters recalibrated, signal thresholds adjusted, and tracking histories reconstructed from partial data. In traditional air defense doctrine, these delays are considered insignificant. A few seconds of recalibration rarely matter when engaging fast aircraft or ballistic threats that remain visible and predictable across multiple radar sweeps. Against drones, however, those assumptions collapse. In this case, the drones were not racing toward the target. They were pacing the system. Their speed and altitude were carefully chosen to ensure that a delay of even 3 seconds allowed them to cross critical engagement boundaries. While the radar was rebuilding its picture, the drones were already somewhere else. When the system regained clarity, it was looking at an outdated reality. The threat had moved, spacing had changed, and the geometry of interception was no longer optimal. This forced the system into a reactive loop, constantly chasing a target profile that no longer existed. What made these reset cycles especially dangerous was their predictability. They were not malfunctions or accidents. They were expected behaviors embedded in the design of sophisticated sensors. The drones exploited this reliability. Missile launches were deliberately provoked, knowing that each response would momentarily degrade situational awareness. During those brief windows, the drones slipped beneath detection layers, altered altitude, or widened their spacing, all while remaining within the physical limits of the environment that masked them from clean radar returns. In earlier eras, air defense was measured by range, speed, and kill probability. In this encounter, it was measured by continuity. The system could see, track, and engage, but not without interruption. Drone warfare turned those interruptions into opportunities. By aligning their movement with the defender's internal reset rhythm, the drones transformed routine maintenance processes into tactical blind spots. The result was not a sudden failure, but a series of perfectly timed pauses that gradually stripped the defense of its ability to maintain control over the battle space. At the heart of this engagement was a counterintuitive reality that challenges long-standing assumptions about air defense. The missiles were simply too fast for the targets they were trying to destroy. Interceptors like those used in this battle are engineered to defeat high-energy threats, jets, and cruise missiles, moving quickly and predictably through open airspace. Against such targets, speed is an advantage. Against slow, lightweight drones creeping through cluttered environments, that same speed becomes a liability. The guidance system struggled to reconcile tiny, irregular movements with the expectation that a legitimate target would travel far between radar updates. Each minor adjustment by the drone forced the missile to correct its course, bleeding energy with every turn. As the missile slowed and maneuvered, its own guidance logic began to work against it. Filtering algorithms designed to ignore insignificant motion near the surface increasingly treated the drone's behavior as noise rather than intent. When a target does not move enough between sweeps, the system hesitates. It questions whether what it is seeing is real or simply environmental interference. Meanwhile, the drone continues forward at a steady, patient pace, remaining inside the very clutter zones that the missile's sensors are trained to distrust. The result was a paradox that modern air defense doctrine has not fully reconciled. The faster the interceptor, the less time it had to interpret ambiguous data correctly. High closing speeds, compressed decision windows, and amplified small tracking errors. In one case, a near miss generated enough overpressure to destroy a drone indirectly, but others slipped through untouched, not because they were evasive in a dramatic sense, but because they were unremarkable. Their lack of speed and energy made them difficult to define as threats in the mathematical language of missile guidance. There is no single correct interpretation here. Some engineers might argue that this is a tuning problem, solvable with better filters or updated engagement logic. Others might see it as evidence that missile-centric air defense is fundamentally mismatched to low-energy threats. What is clear is that this moment exposed an uncomfortable truth. In certain conditions, slowing down can be more survivable than speeding up. Different professionals would likely view this encounter in very different ways, and that divergence itself may be the most important lesson. What ultimately broke the defense was not an inability to detect incoming drones, but an inability to engage enough of them at the same time. The Pantsir system was fully aware of the threat. Multiple targets were tracked, ranges were known, and closing speeds were calculated correctly. The failure emerged at the moment those tracks had to be turned into actions. With only 2 fire channels available, the system was forced to make choices. Every engagement locked the turret and guidance logic into a narrow slice of airspace, creating blind cones elsewhere. Coverage did not disappear, but it fractured, leaving gaps that could not be closed quickly enough. The drones were designed to exploit this limitation. As they approached, their spacing widened, deliberately stretching the engagement geometry beyond what a single system could handle simultaneously. Instead of arriving as a dense swarm that could be addressed in sequence, they presented as multiple, equally urgent problems from different angles. The defenders were pushed into binary decisions: engage this target now and accept exposure elsewhere, or hold fire and risk losing the opportunity altogether. There was no option that preserved full coverage. This is where time pressure became decisive. Each lock consumed precious seconds. Each missile launch committed the system to one direction, while other drones continued to advance unopposed. Even when intercept succeeded, the cost was opportunity. Reload timers, turret repositioning, and guidance resets ensured that no single success could be rapidly followed by another without consequence. The system was operating exactly as designed, but design itself imposed hard limits that could not be overcome by skill or experience. What makes this dynamic especially dangerous is that it does not require overwhelming numbers. A small group of well-spaced drones was enough to saturate the available channels and force defensive fragmentation. The attack demonstrated that modern air defense can be defeated not by blinding it, but by forcing it to look in too many directions at once. In that sense, the engagement was less about firepower and more about geometry. Once the defenders were forced into making isolated decisions under compression, the layered shield lost its cohesion and detection. Without engagement became little more than situational awareness without control. When the automated layers of the defense began to lose coherence, the system fell back on its last safeguard: human coordination. This transition is built into modern air defense doctrine and is often described as a strength. Humans can interpret ambiguity, apply judgment, and prevent catastrophic mistakes. In this engagement, however, that safeguard became a bottleneck. As digital handoffs failed and confidence values dropped, operators reverted to voice communication. Bearings were read aloud, distances repeated, and reference points clarified. Each step added seconds. Individually, these delays were minor. Collectively, they were decisive. Human operators are trained to confirm before they commit. This instinct is essential when the cost of error is high and the battle space is complex. Missile launches cannot be undone, and misidentification can be catastrophic. But drones do not wait for confirmation. They advance with mechanical persistence, unaffected by doubt, fatigue, or uncertainty. While operators debated whether two contacts were the same object or separate threats, the drones closed hundreds of meters. By the time agreement was reached, the geometry of the engagement had already changed, forcing yet another round of reassessment. The mismatch was not one of competence, but of tempo. Humans operate on cognitive cycles, measured in seconds, sometimes tens of seconds, especially under stress. Autonomous systems operate on clock cycles and pre-programmed thresholds. When the automated network fractured and responsibility shifted to people, the pace of the battle slowed at exactly the moment when speed mattered most. The defenders were not overwhelmed by complexity. They were constrained by caution. This dynamic exposes a deeper problem in modern warfare. Air defense systems are designed around the idea that humans can seamlessly step in when automation falters. That assumption holds against threats that behave predictably or remain visible long enough for careful judgment. Against small, persistent drones that exploit every hesitation, it becomes a liability. The attack demonstrated that certainty is a luxury defenders may no longer have. In a battle space where autonomous systems press forward without pause, the very qualities that make human oversight safe and responsible can render it incompatible with the tempo of the fight. One of the most subtle yet decisive elements of the attack was the use of electromagnetic terrain as a form of protection. Instead of relying on hills, buildings, or vegetation, the drone exploited a corridor defined by high-voltage transmission lines. These structures do more than carry electricity. They ionize the air around them, creating a constant corona discharge that fills the surrounding space with electromagnetic noise. To radar systems, this environment is inherently unstable. Signal returns fluctuate, confidence values drop, and filters struggle to separate meaningful movement from interference. By aligning its approach with this corridor, the drone effectively wrapped itself in electronic camouflage. This was not an accident of geography. It was a deliberate choice to maneuver through a space where sensors are least reliable. Unlike traditional terrain masking, nothing physically blocked the radar's line of sight. The target remained technically visible, but algorithmically uncertain. The system could not decide whether the contact was real, persistent, or simply a byproduct of environmental interference. As confidence collapsed, guidance quality degraded. When a missile was finally launched, it did so without a stable lock, relying on estimated bearings rather than firm tracking. The consequences extended beyond a missed intercept. The missile detonated prematurely against a power tower, severing the line and causing a localized blackout. In one moment, the defenders lost both an interceptor and critical infrastructure, while the drone passed through the interference zone unharmed. This compounded effect illustrates how modern engagements increasingly blur the line between battlefield and civilian systems. Infrastructure is no longer just collateral risk. It can become an active participant in the fight, intentionally or otherwise. What makes this tactic especially significant is that it redefines maneuver space. The drone did not need to outrun or outgun the defense. It simply needed to occupy an environment where sensors could not be trusted. Electromagnetic conditions became as relevant as terrain elevation or cover once were. In future conflicts, airspace will not be defined solely by physical geography, but by layers of interference, noise, and signal distortion. Mastery of that invisible terrain may prove just as decisive as control of the ground below. In the final moments of the attack, the drone no longer depended on anything outside itself. No radar emissions, no GPS corrections, no data link commands guiding its path. What remained was terminal autonomy, a phase where the system stopped communicating and started deciding. As it crossed into the base perimeter, inertial navigation gave way to onboard vision. The environment was scanned in real time. Hangars, aprons, parked aircraft, fuel trucks, spatial relationships, shadows, and alignment. These were not images in a human sense, but data points compared against a stored priority library built long before launch. The selection of the AN-26 was not improvised, nor was it directed remotely. The aircraft matched a set of criteria: size, roll exposure, and contextual value within the immediate environment. It was stationary, unprotected, and positioned near secondary assets that could amplify damage. Within fractions of a second, the system resolved ambiguity and committed. At that point, no defensive measure still in play could meaningfully interfere. Guns relied on visual tracking but lacked precision. Electronic countermeasures had nothing to jam. Missiles required radar confidence that no longer existed. The decision had already been made, and the outcome followed. This moment represents a quiet but profound shift in warfare. The strike was no longer an extension of a human operator's intent in real time. It was the execution of a pre-authorized logic chain that unfolded independently once conditions were met. Autonomy did not mean randomness. It meant insulation from disruption. By removing external dependencies, the drone became immune to the very defenses designed to break connections, blind sensors, and sow confusion. What makes this especially consequential is not the technology itself, but the precedent it sets. The engagement ended not with a contest of reaction speeds, but with a comparison of decision models. One side relied on layered systems requiring coordination, confirmation, and synchronization. The other relied on a single platform capable of acting alone when everything else failed. If you value objective analysis over speculation and noise, consider following this channel. We focus on how decisions are made and how those decisions are reshaping the battlefield. The destruction of the AN-26 was not the result of broken equipment or inadequate technology. It was the outcome of a cognitive failure rooted in doctrine. Modern air defense systems are built around a hierarchy of threat values that has remained largely unchanged for decades. Bigger targets are considered more dangerous. Faster targets demand faster responses. Higher altitude implies greater reach and urgency. These assumptions shaped every automated priority, every engagement rule, and every human expectation during the defense of the airbase. The attack succeeded by quietly violating all of them at once. The drones were small, slow, and low qualities traditionally associated with low threat. They did not rush the defenses or announce their presence with dramatic maneuvers. Instead, they advanced patiently, exploiting hesitation rather than provoking panic. Ambiguity became their greatest asset. Each moment of uncertainty forced the defenders to question what they were seeing and whether it justified action. By the time the threat was fully acknowledged, the decision space had already narrowed. This was not a failure to respond. It was a failure to recognize that the rules for response no longer applied. What makes this loss strategically significant is that the defenses performed as designed. Radars detected missiles, launched, guns fired, and operators followed procedure. Yet those procedures were optimized for a world where danger scales with size and speed. The drones operated in a different logic space, where persistence outweighs velocity and confusion outweighs force. The defense expected threats to behave in familiar ways. When they did not, the system had no intuitive framework to interpret what it was facing. This reveals a deeper vulnerability than any technical shortcoming. Technology reflects the thinking embedded within it. When doctrine lags behind reality, even advanced systems can be steered into irrelevance. The AN-26 was lost, not because the air defense lacked capability, but because it misunderstood the nature of the threat. Modern warfare increasingly rewards actors who understand how systems think, where they hesitate, and which assumptions they cannot easily abandon. In that sense, the most damaging weapon in this engagement was not the drone's warhead, but the outdated ideas it exposed. When you step back from the technology and the headlines, the deeper lesson here is not really about drones or air defenses. It is about endurance, choices, and the quiet cost of always having to react. In life, as in conflict, Winning a single moment does not always mean you are winning overall. Sometimes the greater danger lies in situations that force you to stay constantly alert, constantly responding, without time to rest, reflect, or recover. Many people reach a stage in life where the pressure does not come from dramatic crises, but from repetition, ongoing obligations, unresolved tensions, or routines that slowly drain energy and clarity. The lesson is that sustainability matters more than intensity. A path that looks manageable day by day can still become damaging if it never allows space to reset. Strength is not only about resilience, but about knowing when a pattern itself is unhealthy. There is also a reminder here about perspective. Real damage is often invisible at first. It shows up quietly through fatigue, stress, and diminishing joy, rather than sudden collapse. Paying attention early before the cost becomes overwhelming can make the difference between maintaining control and slowly losing it. In the end, whether in nations or in personal lives, the question is not, can I handle this today? But can I afford to live like this indefinitely? Recognizing that difference is often the first step toward wiser decisions and a more balanced, enduring sense of stability.